Hello everyone, welcome back. In the last session we introduced ourselves to the different mechanisms by which suspended matter can be removed by different types of filtration. One is depth and one is surface filtration by the membranes. And then we started looking at the aspects relevant to depth filtration. Initially performance is not good, but this is required because that will in effect lead to increase in filter performance during this ripening, right. And after that for 1 or 4 days you are going to have good removal or good removal efficiency with respect to turbidity or decrease in turbidity, and afterwards again you are going to have increasing turbidity and then the run is terminated. And in that context we also saw that this head loss is going to keep increasing, and that is also one factor to terminate it. So, which factor to choose will depend upon which one comes earlier and also the operator's frequency or ease of backwashing due to the operator's convenience, right. So, let us move on here. So, one aspect is that if we do not look at the relevant performance and the relevant backwash, we can even have negative pressure being developed in the rapid filtration or during rapid filtration. So, here we have this water is out here. Okay, let me put it up here because they are starting the head here. Water is at this level, right, and here just water above the media, right. This is what we typically have, and under this head water is filtered through this particular sand. This is the cross section obviously, and this is the media. So, we see this obviously with increasing depth in water, increasing head, let us see, and this is where the media starts. And here we see a curve, and this curve gives us the depth to clean sand, as in initially clean sand is available right here, but with or after operation of the filter over a certain period of time, what is going to happen, this particular initial top layer I guess is not very clean. So, to reach this particular clean sand layer you are going to have to go deeper and deeper. So, that is what it means, curve representing increase in depth to clean sand filter with time or clean sand with time, right. So, that is what is happening. So, what is going to happen during this operation? Head loss is going to increase, that is what you see. This is the head curve with clean filter. So, this is due to the clean filter head loss, not much depending on how you design it obviously, but as you can see here, right, as you are running the plant, first head loss, okay, something like this, and then it goes into the negative zone, right, negative pressure. So, that can lead to air bubbles and such, and obviously considerable issues with respect to or considerable deterioration in your plant operation efficiency. So, obviously you will have to see to it that this does not occur or you backwash it before your head loss is so high, right. So, that is one reason. Other reason is obviously if head loss is too high, obviously your pressures or your energy requirement later to pump it up or such will again increase. So, that is something to keep in mind. Let us move on. So, reverse flow of water. So, we just established the need for backwashing. Usually water flow is this through the media, right, through the media, but we need to backwash it from time to time to decrease the head loss and also prevent this negative pressure from being developed within the depth, let us say within the depth of the relevant filter. So, what do? We are going to have to backwash or fluidize the bed. So, during this backwash what is going to happen to the bed? The bed is going to be expanded. Earlier it was like this and now it is going to be like this. Why? The particles which were compacted earlier, we are pushing them against gravity, so they are not going to be as compacted. So, the bed is going to be fluidized or expanded, right. And in general the total volume expansion I guess of the bed is 10 to 25%. But one aspect to keep in mind is that the mass of the relevant media is still the same, or the volume of the actual media is still the same. Volume of the total bed I guess is increasing, but volume of the media is still the same. That is something to keep in mind, and I believe we will use that later in this or the next session. Expansion is measured with respect to depth because the cross sectional area is the same or surface area is the same. I should not have said cross sectional area. So, with respect to the depth or with respect to volume, let us say in general with respect to the depth. When is more mixing or more level of backwashing required, right? When there is remarkably high turbidity or suspended salt concentration in the influent, meaning a lot of suspended matter has been adsorbed onto my relevant filter media. Obviously one thing. And when else? For example, if I have coagulation before the relevant filtration, or I just did not have sedimentation, I already have this, I already had coagulation or coagulant being added or polymers being added. So then I will have to wash them off too, right? So that's when we will need it. So when polymers are added, that's something you will have to look at. And when else will we have to look at this, right? Okay, what is the mechanism? Mechanism is surface core, as in the surface cleaning too can be done. You will have surface core pipes. That's one way to go about it. So you have fixed or rotating pipes which will provide more wash or additional wash near the surface of the expanded bed, right? So that's one way to go about it. And sometimes you will even pump air in along with this water. So that will give you that additional level of mixing or such that's required, let's say. Yes. Again, where is this backwash water going to come from? So you will typically store some water to be used, or store some treated water to be used for backwash. That also will have to go into account or be taken into account when you are going to design for a particular filter, right? The amount of backwash required and how frequently is that required. So design criteria, obviously. So first aspect is depth, right? How am I going to, what should the depth of the relevant filtration be, and what is that depend upon? Obviously velocity of fluid past the particles, what is the velocity of fluid past the particles or the filtration rate in a way. And why is that important? Because we looked at contacts, how many contacts and how many contacts are leading to removal. So it will affect the contact efficiency, and it will also affect flocculation, as flock breaks up if the relevant speed is too high, let us say, right. So that is something to keep in mind. So depth filtration will have to be taken into account. Well, here is one aspect, obviously. Okay, I wanted to talk about this aspect here, but I see that it is being covered here. Hydraulic loading rate, right. At what rate is the water being loaded? So its volume per area per time, that is why it comes out to be 1 dimension meters per time. Let us say this is R, 4.9 or 5 meters per hour to 7.5 meters per hour if it is single media sand filter. If it is dual or multiple media sand filter, it is relatively high, 12.2 meters per hour to 15 meters per hour, let us say, right. Multiple media sand filter, that is when typically the efficiency increases, right. So we will come back to this, we will look at the design later. So what are the other considerations? Obviously the kind of media and how many layers, or is it single media, 3 kinds of media or multiple media or such, let us see. Let us see when these things come into play. Obviously when I choose media, I need to look at the size of the relevant media, and when I talk about size, I am talking about effective size, as in effective size. Typically the well established norm is that we look at 10% of the particles by weight passing through a particular size, and that size is referred to as the effective size, right. So 10% of the sizes by weight, this is by weight, are smaller than the effective size, which I am referring to as P10, right. Again different nomenclatures. Empirically it tells me, why is that important? It tells me that, or it gives the head loss characteristics in mixed sizes as predicted with single media size model, let us see. Anyway, it gives me an idea about head loss characteristics, right. So that is why we typically look at P10, and then we also look at uniformity coefficient, how uniform is your relevant media, let us see, and that is going to be depend upon P60, P60 measured in the same way as P10, but instead of 10% we look at 60%, P60 by P10, right. And here it is 1.3 to 1.8, right. If uniformity coefficient number is too high, that means that the particles are not too uniform, let us see. I think that is the understanding here, right, as in there is great variation here. And typically effective size 0.35 to 0.6 mm, right. Keep it in mind that it is mm size, and uniformity coefficient around 1.5, right. That is something to keep in mind. So what kind, I mean, this is a figure where they zoomed in, this is from Crittenden et al. So you have coal, anthracite coal here, sand and garnet that is sometimes used. And why is this well rounded? They say that because it is from river sand, so because water has flown around it, So, you are going to have rounded structures or not structures, rounded shapes. They can also, or the vendors can also provide crushed sand depending on the source. That is something to keep in mind, because that will affect your percentage or kind of removal anyway, right. So, filter media type sand, this is the most widely used sand filter. Well, first it is inert and it is typically used when you are only using one media, let us say, yes, and density 2.5 kilograms per liter. If it is dual media or such, you are going to use anthracite above sand, right, relatively less dense, I guess, typically added with sand as I mentioned in the dual media filter. And why is this? It will achieve the size distribution with the larger particles on top, let us say, right, larger particles on top and smaller ones at the bottom. If not, you are going to have issues with respect to head loss and also removal efficiency and particles sinking in, let us say. So, if it is triple media filter, then you can also have different minerals here, garnet and ilmenite again, but here you see that the density is relatively higher. In general, dual media filters with anthracite above sand is the typical or usual way to go about it, and I think we have a picture coming up here. Okay, we have coal, we have graded sand, as you can see, you know, it is visual. You can see the graded sand, different kinds of sand, and then pea gravel and the coarse gravel that form the bed here, let us see. And then this filtered water is collected in this vitrified clay filter block. This is something we looked at in the previous session, right. We have perforated pipes, we have vitrified clay filter blocks which were widely used or maybe still used in many places, and now people are using or moving on to IMS and such integrated media systems. Vitrified clay filter block, let us see. And I guess you can see the water head here, or I can't be sure here, okay, probably no water here, then the water would have flown out. But again, typically you would have the water head out here, yes, and the water under that head will be flowing through this while these particles or while the filter does its job. So, here we have another picture. Again, these are from the student presentations of Mackenzie Davis water and wastewater. So, these you can access to. There are many more such worthwhile pictures which give you an idea about the practical aspects and the aspects of construction or how to construct relevant media or unit process. You can always access them, right. So, gravel layer above the under drain, that is something we looked at, and from the side, I guess, or the section, vitrified clay under drain block, filtered water obviously, as we mentioned, comes out and backwash enters here, right. So, you have these holes, yes, 3 mm diameter drain holes through which the water comes from above into these vitrified clay blocks, let us see. As mentioned, clay blocks were the standard for under drain construction, let us see, right. And different types of what do we say, or properties of filter media, we should have discussed this earlier too. We did discuss density, right, okay, we did discuss that earlier. But let us look at the effective size usually, let us see, right. Anthracite coal widely used, granular activated carbon to use depending upon your relevant objective, and here you have the relevant size, right. This is what we have already looked at earlier, let us see. Uniformity coefficient, you see this level of uniformity coefficient depending on the relevant kind of particle, let us say, right. So, porosity also within a relatively close range, right. Again, why sphericity or such, this is what we talked about when we looked at sand which is well rounded or relatively crushed and irregular, because most of the models looked at or assumed that the media is rounded, and thus the mechanisms and the models depend upon the kind of or the shape of the relevant media. But if it is crushed sand, again you can look at empirical equations or look at the experimental data too, right. So, experimental data versus this, why is this? We want to, or I want to look at the efficiency of removal with respect to the size of the relevant particle. Here on the y axis we have removal efficiency of the filter, and here we have suspended particles, and we see that, as I mentioned earlier too, the particle range around 1 micron, right, 1 micron are relatively difficult to remove by your filtration, at least with respect to the sizes and such that we look at, let us see, right. And again, relevant information is mentioned here. So, experimental data and the theoretical model, what do they both predict? They both predict that the efficiency is lowest for the sizes around 1 micron, let us say, right. So, again here again you can see increase, but it does not mean it is going to keep increasing. There is obviously going to be a limit out here. And why is that? If you look at it, removal efficiency due to inertia, due to gravity or sedimentation, and due to diffusion, let us say, or Brownian motion. We looked at different aspects. I think we looked at interception and such, and we looked at sedimentation, and we looked at Brownian motion, right. So, aspects related to these kinds of removals, let us see, right. So, as you can see, removal efficiency due to interception and due to, or inertia, pardon me, and due to gravity, again it depends upon the square of the diameter of the particle. So, big particle interception typically occurs by these two or by these two ways. With respect to smaller particles, it is with respect to diffusion or due to Brownian motion, right. That is what you see, and thus you see that as the diameter of the particle decreases, the efficiency due to removal by diffusion or due to Brownian motion increases, right. That is what you see out here, and that is also the case that you see out here, let us see, right. Let us move on. So, here we have another figure that gives us an idea about dual media filter. So, sand and then anthracite above it, let us see, and alpha gives you an idea about at the level of chemical treatment or chemical activity, if I can say so, let us say, right. So, what do we see here? Here we have on the left side y axis the depth, and here we have the filter quality, let us see. This is C out by C in, right. So, C out should be as low as possible, that is what you want, yes. So, almost 0 or 1, let us say, right. So, 1 by 100 or such, pretty low. So, what is the first aspects? Let us look at 1 maybe. So, with respect to the case where we have some chemical role to play, or chemistry has a role to play. So, chemically treated, I guess. So, what do we have? We see that even at relatively low depths, you do have some removal, but not a lot of removal. The removal efficiency is relatively poor, right. But with depth, as you can see, the efficiency increases, right, much more, and by the time it reaches the sand, obviously there is a quantum increase, and you can see that the filter quality is remarkably good. Yes, so you can choose your sizes and such accordingly. With respect to relatively less chemical treatment, what do you see? Obviously, again anthracite not doing very well, yes, but from the sand obviously the removal efficiency increases. So, here you can see the role of the chemical treatment, the role of the dual media filter, let us see, right. So, again this is something to keep in mind. Filter media depths typically 60 to 75 meters, minimum is around 60 centimeters typically, and rate of filtration, this is something we came across earlier, Q by the surface area of the filter. I think I already mentioned this. The units are meter cube per meter square per hour. So, effectively they come out to be meters per hour or dimension per time, let us say, dimension per time, rate of filtration. So, head loss at the clean filter. So, just because there is media, obviously that is going to lead to some head loss, and afterwards when filter has been put into operation, we know that filter what we say is, if I can use layman's terms, it is going to choke, or you are going to have the particles being deposited on the relevant media and between the pores, and you are going to have increasing head loss. So, to look at that, let us understand some of the variables that we are going to look at. Obviously, head loss through the filter, approach velocity, right, this is easy to calculate, Q by the surface area, which we just also looked at. So, depth of filter media, shape factor giving us because different shapes, different levels of removal, I think we also discussed this earlier. Porosity of the media, coefficient of drag F and dg, this is the relevant geometric mean coefficient of drag, right. This obviously depends upon the Reynolds number, right. We looked at it, Reynolds number, typically we are concerned with laminar flow when R is less than 1, and then transition flow between maybe 1 to 100, I guess, and then we have turbulent flow later. But in general, in our filtration, what do we say, relevant flows, we are going to have maybe laminar, or most probably during the, this transition flow when Reynolds number is between R and 100. So, this is called the Frockheimer's flow, if I am not wrong, you can check this spelling. Why is this relevant? Because based on the relevant flow, the coefficient of drag will change, and based on that obviously your head loss will also be changing. In general, we are dealing with flows mostly in the Frockheimer flow, let us see, right. Again, we will look at this. Head loss if it is laminar flow will be different, head loss if the Reynolds number is in this zone will be different. So, that is something to keep in mind. Again, do not think or look at me for the reference for this particular spelling, you should check the spelling, right. When the Reynolds number is relatively less and Reynolds number in the transition or particularly in the turbulent zone, I guess, right, turbulent flow conditions, but rarely will we get that, right. You can calculate Reynolds number obviously, and in this course I will give the relevant equations and such in a sheet, at least for this course, but depending upon which exams you want to pass and such, they might need you to mug up relevant stuff, let us see, right. So, this F is the mass fraction of particles in the layer, fraction of particles or mass fraction of particles in layer. As I mentioned, D with the subscript G is the geometric mean diameter of the particles in the layer. So, when we say by sieve analysis, D1 and D2 are the sieve size openings and then they retain a layer, then dg is equal to square root of d1 d2, let us see, right. So, again this is something that we have looked at. You have different size, the relevant particles or the filter media is passed through sieves of different size. Depending upon the need, you will look at different sieve sizes and you will look at the size of the sieves and the fraction that is retained, right, and then you will be able to get your geometric mean diameter. Okay. So, what else do we have? K is equal to the filtration constant, capital K is head loss coefficient due to viscous forces, head loss coefficient due to inertial forces. This is something to keep in mind, due to viscous and due to inertial forces, let us say. One is predominant during laminar, one is predominant during the flow Frockheimer's flow between the Reynolds number is between 1 to 100, let us say, right. That is something to keep in mind. L is depth of filter bed, P is fraction of particles again based on mass within adjacent sieve sizes. S is the shape factor, which again this is a different set of notation used by a different set of books, but I wanted to give both the notations. We have also seen this earlier. Kinematic viscosity, density of water, right. Okay, let us move on. So, Rho's equation, let us see, right, and this is when you have laminar flow conditions, laminar flow, Reynolds number is less than 1. And for that laminar flow conditions, we have this Vf is equal to K HL by L. HL is your head loss, let us see, right, and K is your hydraulic conductivity dimension per time, let us see. And from this you can calculate your head loss, and more or less from that we have the Rho's equation out here, let us see, again for laminar conditions typically. Yes, see that it is V square here, that is something for you to keep in mind. And then we have Karman-Kozny equation. This is for spherical or spherical granular media and laminar flow, right, spherical what do we say, granular media and laminar flow, right. That is something to again keep in mind. Again, you do not need to mug these up, at least for this particular class, let us see. Again, Reynolds number calculation based on the relevant variables that are relevant to filtration are given here. Fairhatch equation again takes into account, I guess, non-spherical filter grains, let us see. Again laminar flow, but again here we have non-spherical. So, here spherical and non-spherical. So, this is the case, or you have this Ergun equation where you have two independent terms that will give you an idea about why or not why, when to choose this equation. This is the one when we have Frockheimer's flow, when Reynolds number is between 1 and 100, let us say, right. And for this head loss, I guess will be depend upon two aspects. One is K1 into V square and the other one is K2 into V, I guess, right. Okay, so that is what you see here. Yes, so when you see something like this, that means this is for the case when you have relatively faster velocities at play, and thus it is not laminar conditions, but maybe transition flow. Yes, if not transition, just about reaching transition, again Frockheimer's flow, let us see, head loss is this. So, that is why you have two terms, one with VA and one with VA square, let us see, right. Again, as can be seen, this is for head loss through granular media at higher filtration velocity or with respect to the Frockheimer's flow that we talked about earlier, let us see. This is the Ergun equation. Yes. So, let us see what we have. So, we are asked to calculate the clean bed head loss. This is the clean bed head loss through a deep bed anthracite filter with 1.8 meters of effective size is equal to 0.95 mm media at a filtration rate of 15 meters per hour and a temperature of 15 degrees centigrade, let us say, right. Effective size and deep bed of 1.8 meters, this is given. So, let us see what to go about it. So, we have the relevant constants which are given, if not you will have to look at the relevant table, porosity and such. Let us move on. So, here we are using the Ergun equation, expecting it to be the use for a rapid sand filter. The expectation is that it is being used for a rapid sand filter. If it is typically deep bed, right. So, you are going to look at relatively greater depths, again that is when you will, or the reason is because you are going to use them for rapid sand filtration, let us see. So, that is why we are looking at rapid sand filtration and using this particular Ergun equation. So, let us see what we have. So, first term again just simply plugging in the relevant aspects, right. You can look at these variables, and if there is an error you can always change the calculations, but it is just based on plugging in the values mentioned earlier. But we will see why we are looking at this, let us see. So, one is 0.44 first term, second term comes out to be I guess 0.06, 0.44 and 0.06. So, why is this that we are looking at this particular equation, not equation, relevant data? As you can see, a relatively small contribution to the head loss comes from the inertial term. Inertia term relatively small, I guess. Yes, let me make sure that that is the relevant case. So, first term again diameter square, and here second term diameter, again velocity and such, let us see. As we can see, the inertia relevant term, right, inertia relevant term is relatively less, but it becomes important for larger media, right. It becomes important for larger media and higher velocities, larger media and higher velocities used in high rapid sand filters, let us say, high rate rapid filters. And as we can see, Crittenden et al. Tells us that if the filter media is designed for 2.5 meters of available head, right, 2.5 meters, and out of that 0.5, that is a lot of head loss, right. The clean bed head loss itself consumes around 10% of 20% of the available head. So, that is something to keep in mind, right. So, let us move on. So, backwash, again I think I have pictures at this case, okay. So, sand filter schematic with different backwash troughs. So, what do I have here? We have the section and we have the under drain, and we are going to pump the water up. During that time obviously you are going to have a fluidized bed. The bed is not going to be like this, there is going to be an expansion of the bed, and then this waste water is going to be, or backwash water is going to go through this, or going to be collected through these backwash troughs. During operation though, obviously the water flow is in this direction and not in this direction, right, and during that obviously you need a standing head of water. And also you can see these arms, right, these arms which are required for cleaning the surface. This is what we mentioned when we talked about additional mixing or additional level of removal, let us see, right, additional level of mixing when we have polymers and such. These are for surface cleaning, and here you see the surface. And again different what do we say, total head here, yes. So, in general what do we have? We have a fixed bed, right, relatively well packed, but during backwash it is going to be relatively expanded here. Fixed and expanded beds during backwash. During filtration obviously they are touching each other, right, touching each other, but when they are fluidized, that is why we call that fluidized, let us say, right. Fluidized during backwashing, the void volume increases, causing an overall expansion of the bed. But as you can see, if I look at it, the same what do we say, the volume of the media is still the same. That is a principle we are going to use later. Volume of the media is still the same, but volume of the bed is going to increase, let us say. Let us move on. So, what do we see here? Here they are going to begin backwashing here, let us say. These are the backwash troughs, okay. They are just about to start backwashing, and this is where you have the relevant filtration occurring, but they just started pumping water in the reverse direction, I guess, right. So, water is going to come out from here and go into this backwash, or be collected in this backwash troughs. So, cloudy water on either side of the backwash trough. Why is this? This is alum floc and particulate matter. Looks like before this they had relevant coagulant being added, which was alum. So, when they are backwashing it, you see that this cloudy material is alum flock and some particulate matter on the surface, and obviously from the backwash straw it is being collected in the gullet, let us say gullet. And now after backwashing is continued, more of the particles that are adsorbed, right, are going to now be desorbed, if I may say so, and they are going to come out here. Backwash continues and water becomes cloudy and colored with soil particles. So, that is what you see here, right, and then it is going to be collected in your particular backwash troughs. So, okay, we also see foaming from organic matter, we see that, and the backwash water, now you see it is relatively clouded or pretty poor in quality. And how long will I do that? Well, it depends upon what do we say the level of treatment, but one thumb rule is if you are doing that manually, you can look at how clean the water is, but again rarely is that done. So, you can see that it is still cloudy, but after some operation you see that it is relatively clearer. So, now is the case, and after some time water is starting to become relatively clearer, let us say, right. And back again after more continuous backwashing, water is the backwash water is starting to become relatively clearer, meaning the filter is relatively cleaner now, right. And backwash continues to show foaming, that means there is still organic matter that is taking longer to desorb, right. Backwash now continues to be clear, and looks like in this case they were the backwashing rate was too high, and that is why it is leading to a backup in the backwash straw. You can compare that with the figure here and then this backup. So, this is something you want to avoid obviously, right. So, backwashing will continue until the backwash water is clear. You can have what do we say automated ones, but again as you can see even manual backwashing with manual judgment is also relatively decent enough, let us say, right. So, design criteria with respect to backwash, what is it that I need to be concerned about? So, the first aspect is that the backwash velocity must be lower than the settling velocity of the smallest media particle. Why is that? If not, I am backwashing it, and when I am backwashing it, the particles are not compact or settled anymore, they are fluidized, but still gravity is going to pull them down. If I increase the backwash velocity to a certain value or beyond a threshold, what is going to happen? This particular particle which is trying to settle down, the media which I want to retain, I do not want to lose this filter bed media, right, is also going to be removed with my backwash. So, obviously this backwash velocity should always be lower than the settling velocity of the smallest media particle, right. So, that is something to keep in mind, and we will look at the aspects relevant to head loss and also solve a relevant what do we say an example in the next session. With that, I will end today's session.